Okay, so Le Chatelier's principle. When a system at equilibrium is disturbed by a change in a property, the system adjusts to oppose the change. Example of properties are temperature, pressure, and concentration. So if there's a disturbance to a system that's already at equilibrium, there's going to be a shift in the equilibrium, which is a change in the concentration of the reactants from products. The shift moves to oppose the disturbance to reduce its effect. So if you look at this little graph down here, you can see that initially we have an equilibrium. And we know this because these areas are level, they're horizontal. And then there's a change to the system, and you see the net effect. So that would be the curved parts, how it responds, and then a new equilibrium is established, and we know it gets there because again they level off, and basically the concentrations at the new equilibrium will be different than the initial equilibrium because of the change that's occurred. So if you look, this is where the change has occurred. Can you identify which compound or element, which species here, had the change made to it and the other two responded? So the change actually happened with the hydrogen, and we can see that because it's a sharp change. The nitrogen is a gradual, and so is the ammonia, and that's because of the curved part. There was a spike here in the concentration, so some hydrogen was added to the system. So maybe it's a reaction vessel. Some hydrogen was added. So that's our disturbance, adding the hydrogen. And then there's a shift in the equilibrium. So the shift moves to oppose the disturbance. So if hydrogen was added, the opposite of that disturbance is to use it up. So hydrogen will go through a change where it's used up. So the reaction's occurring to use up the hydrogen. Because the reaction is this, because we're using up this, we're pushing the equilibrium to the right. We are going to end up, we want to decrease the amount of hydrogen, so to do that we have to shift to the right and make more products. To do that we also have to use up N2, so that's why here we see a decrease in the concentration of nitrogen, and as a result we should see an increase in the amount of product, and we do. It's gradual. And then a new equilibrium is established. So the shift to the left or the right is talking about where the arrows are. Is it going to shift towards the reactants or to the products? If it's to the products, it's going to be shifting to the right, and if it's reactants, it's going to shift to the left. So we're going to talk about shifts to equilibrium. Okay, so changes in concentration. I'm going to use the ammonia reaction, the Haber process, in this example. So at equilibrium, we've got a certain concentration of hydrogen, nitrogen, and ammonia. And they are constant. They're not changing. And that has to do with the fact that it's a dynamic equilibrium. So our K expression is given here. We put a C here because our equilibrium expression is talking about concentrations. So the C just stands for concentration. You could just put a K. So if nitrogen is added, then the system is no longer at equilibrium. To reestablish, some nitrogen reacts with hydrogen to form ammonia. So we say it's going to shift to the right. So if we increase this one this time, some of this gets used up and we produce more product. The disturbance is the increase in nitrogen. The system moves to oppose this change to decrease the nitrogen. So that means products are going to be made. So here's some scenarios. If you increase the hydrogen, the system will shift to the right to use it up. If we increase the amount of ammonia, if we put in some ammonia into the reaction, then it will have to shift to the left. We would make more reactants. And that's because we want to decrease the amount of ammonia. If we decrease the amount of ammonia by removing some of it, the system will shift to the right to increase it again. If we decrease hydrogen or decrease nitrogen, the system will shift to the left to replace them. So if we remove, the system will replace, and if we add, the system will use up. So at equilibrium, if the disturbance adds, we will shift to remove it. So this is how we can drive reactions to completion. So I've talked before about ammonia and how we have the reaction stops and we have nitrogen and hydrogen and ammonia present. So in order to make more product, you have to figure out how to push the reaction to the right, to the products. So we talk about driving it to completion. So if we continuously remove the ammonia, we're forcing the equilibrium to shift to the right to replace it. All right, changes in pressure and volume. So this has to do with Boyle's law, and basically the concentration of the gas will cause a change in pressure. So concentration is moles per liter. So therefore, pressure will change inversely proportional to the change in volume. So if the volume decreases, pressure will increase. If the volume increases, pressure will decrease. So what you have to do is you look at your subscripts and you find all the gas states and you add them up for the reactant side and separately for the product side. So on the left, we add up the coefficients and we have 4 moles, 3 plus 1. And on the right side, we have 2. So basically, we can say that this side has high pressure and this side has low pressure. And that's just based on the number of moles of gas. So if the volume is changed, there will be a change in pressure, and the system will no longer be at equilibrium and will shift to reestablish it. So when you start a question that has to do with pressure changes, you first have to do this, designate a high and low pressure side for your reaction. So if we double the volume, the pressure will be halved. And that's because if it's 1 over V is equal to P, if we double it, 2 is the number that we represent with double, so the pressure is halved. So the pressure decreases if we change the volume to double it. So the change in the system is we've doubled the volume, which causes a decrease in the pressure. So the system will shift to increase the pressure. So it will shift to the side with the highest number of moles of gas. If the volume is decreased, maybe it's halved, so the volume is halved, then basically we end up doubling the pressure. So In that case, doubling the pressure, the system shifts to oppose it, so it will move to the side with the lowest pressure. So this basically summarizes it. If you increase the pressure by decreasing the volume, it will shift to the direction that has the low pressure, fewer moles of gas. If you decrease the pressure by increasing the volume, the reaction shifts to increase the pressure. If there's equal number of moles, then pressure changes, volume changes will have no effect. So here for this one, H2 plus I2, 2 moles on the left, 2 moles on the right. So this will only be for those chemical reactions where you have subscript G for gas. So if we go to this equation, 3H2 plus N2 goes to ammonia. Okay, so this is our low, this is our high pressure. So if I decrease the volume, that means my pressure is increased. So I've got an increase in pressure, so my system will shift towards the low pressure. If pressure is increased, that's the change, I'm going to move to the right for this equation. So I will increase the concentration of ammonia. If I increase the volume, which means I decrease the pressure, then I'm going to shift to the left because I will want to increase the pressure. So that will result in an increase in H2 and N2. So this one shifted right, this one shifted left. So remember, you're always opposing the change. Changes in temperature. You're going to kind of treat this in a similar way to concentration. If you have a thermochemical equation, you're going to look at it as in an increase in temperature is an increase in the energy, and a decrease in temperature will be a decrease in energy. So an endothermic reaction has the energy on the left-hand side. An exothermic has the energy on the right-hand side. But how you deal with temperature change will be basically the same net effect. So if we increase temperature, the system will move to use up that energy. So the system will respond to an increasing temperature by shifting to the side away from the energy to use it up. So it will go to the opposite side of energy. If we decrease the temperature, then we have to replace energy. So it will shift to side with the energy because you're replacing it. So if we look at the endothermic reaction, if we increase temperature, the system will shift to the right because we're using up that energy. If we increase the temperature in an exothermic reaction, it will shift to the left because it wants to use up that energy. If we decrease the temperature, the system will shift to replace the energy. So it will shift to the side that the energy term is on. So for an endothermic reaction, if we decrease the temperature, we're removing some energy, so the system will shift left to replace it. If it's an exothermic reaction, if we remove some of this energy by decreasing the temperature, the system will move right to replace it. So think about the placement of where the energy term is. I think I need to point out here that changing the temperature is the only change on a system that can affect the value for K, and it's related to how the equilibrium will shift. Okay, so if we look at both of these reactions, and let's say the temperature increases. If we increase the temperature, our endothermic reaction will shift to the right, so there will be more products. That means our K will also increase because K is a ratio of your products to your reactants. So if I've got more products, K will be a larger number. And if we look at the exothermic reaction, if we increase the temperature, that means it will the reaction will shift to the left, which means we end up making more reactants. So shifting to the left means we have more reactants, which means the bigger portion is on the bottom, so the ratio gets smaller. So if we increase the temperature for an exothermic reaction, the K value will go down accordingly. Now, if we decrease the temperature, then for the endothermic reaction, we're removing this energy, so we're lowering the energy, so the system will shift to the left to replace it, which means we will have more products. So this number will be larger, which makes the ratio smaller. When you divide by a bigger number, your ratio gets smaller. So in this case, our K will get smaller. And these make sense because it's a mathematical relationship. So then the opposite should happen for our exothermic. If we decrease the temperature, if we remove energy, the system wants to shift right to replace it, which means we make more HCl, which means this value here on top is larger, which means the ratio is larger. So our K will increase. So temperature will affect your K value, but that is the only change to the system that will affect your K value. So basically, when heat is added, the system shifts in the direction away from the side that the energy term is on, and when heat is removed, the system shifts in the direction towards the side that the energy term is on. Catalyst. A catalyst will have no effect on the equilibrium concentrations of K. They just basically lower the activation energy, so they increase the rate at which equilibrium is reached, but it will not affect K. Sometimes you'll be given an added inert gas like nitrogen or a noble gas. Nitrogen, of course, only is inert if it's not part of the chemical equation, so that wouldn't work for ammonia. But nitrogen gas is a pretty inert gas if it's not part of the chemical reaction. But adding an inert gas has no effect on equilibrium because there's an equal chance that any particle will collide with it. So just the overall pressure changes, so there's no change on equilibrium. So questions where a catalyst is added or they've added an inert gas will have no change on the equilibrium. So sometimes a question will give you a reaction and say, what happens if you change this? What happens if you increase this? What happens if you decrease this? And you have to say whether what the net effect is of the equilibrium. So, for instance, what happens if we decrease the amount of hydrogen? So the system will shift to replace it if we remove it. So the system here will shift left, and that is to replace H2. What happens if we increase the concentration of nitrogen monoxide. Well, the system will shift to oppose it, so if I've increased it, it wants to decrease it. So in order to decrease it, I have to react it. So this one would be shift right to use it up. So take a look at this question and come up with at least 3 ways to increase the amount of nitrogen gas that's formed. 3 ways to increase the concentration of N2. Perhaps it's our product. Maybe that's what we want to produce to use in another reaction. So pause the video, write some down, and see what you come up with. So basically, to do this, you could remove it because the system will shift right to replace it. You could remove water vapor because the system will shift right to replace it and therefore increase nitrogen as well. You could add nitrogen monoxide or hydrogen gas because the system will shift to use them up, which means react, which means it will force it to the right. The total moles of gas on the left is 4. The total number of moles of gas on the right is 3. So nitrogen lies on the side with low pressure. So if we increase pressure by decreasing the volume of the container, the system will shift to the right to oppose the change. So if we increase pressure, the opposite of high is low, so it will shift to the side with a low pressure, so the smallest number of moles. And heat. If we decrease the temperature, it's like removing the energy, so the system will shift right to replace the heat. So these are many different ways to manipulate the system in order to drive the reaction to the right. Chemical engineers really have to have a grasp of this, because if you're making a product, you want to do so in the most cost-effective way possible. And if your reaction stops and you're not maximizing your yield, you've really got to figure out how to manipulate it in order to do that.